This is question 4 for the for my midterm makeup. So we have a thin rod of length L, and it's carrying a charge Q along its length, and at point P, this first question is asking what the direction of the electric field due to this line of charge is, assuming that Q is positive. So if Q is positive, then that means we know that the electric field has to point away from the charge. So we also know that this Q, this rod, is going to be made up of a bunch of fairly small little segments of space that will contain the charge. And if we add all of those little segments up, it's going to produce a bunch of it's going to sum up a bunch of electric fields pointing away in the y direction from the line of charge and away in the negative x direction from the line of charge. And since there's no symmetry argument here, there's not going to be any canceling of components. So we're going to have EY and EX, and that is going to give us our E. And then we can rewrite that here. So at point P, we have this as our electric field. It's pointing away, and it's the result of the y and x component. For question B, we have to write an algebraic expression for each of the components. So since we already wrote this out, we have a bunch of y, we have a y component, and we have an x component. And we can put magnitude signs here and see that we can find EY and EX using trig. So let's do sign first. So due to SOHCAHTOA, so EY over E is going to be equal to sine theta. So this. That'll be our y component. And then we have cosine, which is adjacent over hypotenuse. Those are our two components. And then for our next question, it asks us to set up the integral we need to find the electric field at this point. So again, we have our infinitesimally small dx, which is going to be a distance x away from the point charge, which this is important because the x is what's changing. That's why we need an integral, because as x changes, the electric field in the x direction is going to change. So if we draw r, the distance r from P, or the distance r between P and the dx, we get that dq has not DQ, my bad, DE, this is DE, the electric field due to that small segment of the rod will have components of EY, and EX. So now we can set up our integral, but actually before we do that, we need to understand what dx is, or understand what dq is. So dx has a really small amount of charge because this is a uniformly distributed, this has a uniformly distributed charge. So based on this equation, which the linear charge density is equal to Q over L, then that means that dq would be equal to lambda times an infinitesimally small length, which is dx. So now we can see that quickly. We know that the electric field vector will be equal to the x component and the y component. So we need to find EX, DE. So we need to find DX and DE, or DEX and DEY. So to find DEX and DEY, we can use these equations that we found in question B. So EY is going to be equal to sine theta times the magnitude of E, which the magnitude of E will be DE, the magnitude of E due to this small amount of the length, will be equal to KQ, in this case DQ, over R squared. We also can say that dq is lambda times dx over R squared. Now that we have that, we can find dy and dx. So dey will be equal to sine theta, because of this equation here, sine theta times k lambda dx over R squared. And we have to figure out what to do with this sine theta, which we can just say that we can see from here, which this angle will be the same, so we can kind of find sine theta by using this relationship, that sine theta will be equal to y over R. Also, cosine theta will be equal to x over R. Also, R will be equal to the square root of y squared plus x squared. So now we can plug that in, and we'll get that dy is equal to we combine both of those r's, and now we have r cubed. So now I'm just gonna plug in r now. Now I'm going to put it to the 1/2, which is the same as square root. Nice. So now all we need to do to find EY is integrate it. Now we can find the integral of this here, which let's first maybe take out the constants, stuff that we know. Oops. Did that twice already. Okay. Times the integral of dx over squared. There we go. It's all of our constants taken out. And we can actually replace lambda with q over L. Now all we need to do is set the limits of integration, which if we set this as the origin and this as L, we can say that the limits of integrations are from 0 to L. Now we can repeat this process for the x component. So dx will be equal to cosine theta. I'm going to replace lambda here. R cubed will stay the same, so I simplified everything for time's sake, but R cubed will be the same for both of these equations. The only thing different is that here we have an x and here we have a y. So in the DE or EY we have a y. But in this case we have to integrate that x. It is on the axis of it's what we're integrating. So now if we find EX, get that it equals, take the constants out, same limits of integration. Oops, we forgot dx here. So now we have EX, and now all you would need to do is solve for this integral and these integrals and combine them because as we set up here, E will be equal to EX plus EY. We can take the constants out just to simplify the equation fully. They both of these EY and EX both have KQ over L. So we can take that out and have plus Y, because that is not constant between them, And that'll be our electric field at point P.